Section 16.7, Surface Integrals. Suppose that a surface S has a vector equation R of uv equal to x of uv I, y of uvj, plus z of uvk, where uv is in D. Then the surface integral over the surface S is the limit of the double Riemann sum of f of pij star delta sij, where the areas delta sij are of patches of S that correspond to subrectangles Rij with dimensions delta u and delta v, with the points pij star sample points in each patch. So this is pretty much the same as when we figured out the surface area for a surface. What we would do is we would look at a corresponding parallelogram to some patch in the surface that corresponded to some area in our domain that the surface is floating over. And in this case, it's not really floating over it because R takes it from the UV plane to the surface, but the idea is pretty much the same. We look at this little patch. So we need the surface area of that patch to create our surface integral. So the surface area for each of those patches is these little delta Sij's, and remember that the area of each of those parallelograms was the length of the cross product of the tangent vectors that you make. So that's what we need for our surface area, so that's what our delta Sij's become. And then f of our sample point is just f of r of uv. So this is very similar to the way that we define line integrals. We define line integrals using a little delta s for arc length, where that was the length of the derivative, but because we're in 2 dimensions now for area, we need the length of the cross product of the partial derivatives. So this means that if we take the surface integral of 1, then that's equal to just the surface area. So how about we compute the surface integral x squared ds? Notice, by the way, all surface integrals have a capital S instead of a lowercase s. The capital S is for the surface, whereas the lowercase s was for arc length. Notice that we integrate over s and not over c, like we did for line integrals. So in this case, we have s as the unit sphere. So it's similar to the way that we computed line integrals by parametrizing our curves. We're going to parametrize our surfaces, and that way we can get our surface area, that partial derivative cross product length, and we can plug that in. So in order to parametrize our unit sphere, we'll use spherical coordinates. So in this case, rho is equal to 1 because the radius of the unit sphere is 1. So when x is equal to rho sine phi cosine theta, rho is 1, so that'll just be sine phi cosine theta. And we did this parametrization already in section 16.6. I think it was example 4. So we keep going. We have sine phi cosine theta for y, and we have z equals cosine phi. And phi goes between 0 and pi, and theta goes between 0 and 2 pi. So now we want our vector equation r. So that'll be r of phi theta, and we build it out of each of these components. So the x component is sine phi cosine theta I, and then we've got sine phi sine. Oh, I wrote cosine twice. That should be sine. So sine phi sine theta for rj, and then cosine phi for k. Okay, so then we calculated in section 16.6, example 10, that the cross product of r phi and r theta is just equal to sine of phi. So this means that we have enough now that we can plug into our surface integral. We'll get that the surface integral of x squared ds is equal to the double integral over d of sine of phi cosine theta squared because that's what x is. And then we have to multiply by ds, which is the surface area, so that's r phi crossed with r theta dA. So if we use our parameterization, that means we've got phi and we've got theta. So on the outside I'll have theta going between 0 and 2 pi, and on the inside I'll have phi going between 0 and pi. And then we'll just distribute our square a little bit, so we'll get sine squared phi, and we'll get cosine squared theta. And then we said that this was the length of our cross product, so we'll throw that in there, sine phi. And we are integrating with respect to phi and then with respect to theta. So then this is equal to the integral from 0 to 2 pi of cosine squared theta d theta times the integral from 0 to pi of sine cubed. So this is just the integral from 0 to 2 pi of half 1 plus cosine 2 theta for the cosine squared using our half angle identity. And then for sine cubed, how about we write that as sine times sine squared, and that means that sine times 1 minus cosine squared. So that's just the same thing as sine minus sine times cosine squared. And this is a great way to evaluate sine cubed, because this way we have sine, which is easy to take the antiderivative of, and we have a cosine squared with a sine next to it, so it's an easy mental substitution. So we get half of theta plus half sine 2 theta, where theta goes between 0 and 2 pi, and we get minus cosine phi plus 1/3 cosine cubed phi, and that goes between 0 and pi. So we do the math and we get 4 pi over 3. If S is a surface with equation Z equals g of xy, so that is, S is a surface where Z can be written as a function of x and y, so we have the graph of a function, then we have another formula for our surface integral where the arc length becomes 1 plus each of the partial derivatives of that function. Notice you can't write this if you don't have Z equal to a function of x and y. So this is pretty quick to prove. Any surface with S with equation Z equals g of xy can be regarded as a parametric surface with parametric equations where our x and y's just become the two parameters. So then we take partial derivatives and we get that the partial derivative with respect to x for r is just I plus the partial of g with respect to x k. Notice j is gone because the partial of y with respect to x is 0. And then similarly over here we get j plus the partial of g with respect to y for k because the partial of x with respect to y is 0. And then our cross product becomes this when we take it. So that means the length of the cross product is this. It's pretty much the same formula we got when we were doing surface area. We're just applying it to surface integrals now to throw it in. So how about we evaluate this surface integral right over here of y ds, where s the surface z equals x plus y squared, x goes between 0 and 1, and y goes between 0 and 2. So remember, we're not integrating this surface itself, we're integrating over the surface. The thing we're integrating is actually just y. But so y is floating above, or not really above, but y is floating somewhere else, and then we integrate over this surface itself. So we're not just getting the surface area. The surface area is just one component of our surface integral. That's not just the interpretation of it in general. So we have partial of z with respect to x, that'll be 1, and we'll have partial of z with respect to y equal to 2y. Be careful, my partials look a little bit like my 2's. So now we'll have the surface integral of y ds equal to the double integral of y times the surface area, so that'll be 1 plus the partials squared. So that'll be partial z with respect to x squared plus partial of z with respect to y squared, and we'll throw in a dA. So then this becomes the integral from 0 to 1 for x, integral from 0 to 2 for y of y times square root, 1 plus, well, partial z with respect to x is just 1 we calculated, and this guy's just 2y, so that's 4y squared, and then we'll have dy dx. So that'll be equal to the integral from 0 to 1 dx, because we have no x's there, times square root of 2. We can pull out because add these guys, factor out 2. So we'll be left with the integral from 0 to 2 of y times the square root of 1 plus 2y squared. And that'll become the square root of 2 times 1/4 times 2/3 times 1 plus 2y squared to the 3/2, evaluated from 0 to 2, which is 13 rad 2/3. If S is a piecewise smooth surface that is a finite union of smooth surfaces S1, S2 through Sn that intersect only along their boundaries, and the surface integral of f over s is defined by the sum of each of those surface integrals over each of those surface pieces. So what we do is pretty much the same thing as we do when we have line integrals over a piecewise smooth curve. We just compute all of those separate line integrals. So in this case, we just compute all of those separate surface integrals and then add them together. So how about we do an example and evaluate this surface integral, z ds, where s is the surface whose sides are given by the cylinder, S1, bottom S2 is the disk in the plane, whose top S3 is that part of the plane z equals 1 plus x. Let's see if we can draw this. So it should be some sort of cylinder that's getting like sliced through at an angle at the top. So I'll try to draw the slice kind of like that. And let's say I need a base for this thing. Oops. Maybe I should try drawing it down over here first, and then try drawing my base. Okay, roughly that. And we need a z-axis poking out. And we're gonna need our other axes. Notice the x-axis is actually going to be over here, and the y-axis will be over here. We have to rotate our axis a little bit so that we can actually see this thing. And let's see, we have S1 is the cylinder, so that's this thing over here, and that's x squared plus y squared equals 1. And then we have S2 is the disk on the bottom. So this is S2. And then we have S3 is the plane slicing through at the top. So that's z equals 1 plus x. Okay, so that means we need to compute these 3 different surface integrals and then add them all up. So how about for S1, we need to parameterize that. but we did that parameterization already in section 16.6. That was our cylinder. We did an example 5. So we said x is equal to cosine theta for a cylinder, y is equal to sine theta, and we just let z equal z. So our parameters were theta and z. So we said theta can go from 0 to pi, 2 pi, and z goes from 0 to 1, or in this case 0 to 1 plus x. So that's what z ends up going to over here in this case. So that's just going to be 1 plus cosine theta, because we said x is cosine theta. So now we need the cross product so that we can get our surface area for our surface integral. So our parameters are theta and z, so we'll take r theta cross r z. Let's see, we have to do minus sine theta, cosine theta, and 0 for r theta, 0, 0, 1 for rz, because notice that both of these guys are 0 when you take their partials with respect to z, and this one's 0 when you take the partial with respect to theta. So we'll just throw in our I, j, and k, and we'll take our determinant, and we get cosine theta I plus sine theta j. So that means that the length of this cross product, r theta cross rz, will just be the square root of cosine squared theta plus sine squared theta, which is 1. So we'll take the surface integral now, because we can do it over S1 of z ds, and that'll be the double integral of c times the length of the cross product r theta crossed with rz dA, and that's the integral from 0 to 2 pi, integral from 0 to 1 plus cosine theta for z of z dz d theta. So that's just the integral from 0 to 2 pi of half 1 plus cosine theta squared d theta, because we're throwing in the length of our cross product, which is just 1, and then when we integrate, this is just z squared over 2, plug in 1 plus cosine theta, and that's it. So get a little more space and continue. We'll get half of the integral from 0 to 2 pi of 1 plus 2 cosine theta plus half 1 plus cosine 2 theta by just foiling and then using our half angle identity. And this becomes 1/2 times 3 over 2 theta plus 2 sine theta plus 1/4 sine of 2 theta from 0 to 2 pi, which is 3 pi over 2. So this means that that's our surface integral over S1. Notice that the surface integral over S2 just has z equal to 0 the entire time. So that's a really easy surface integral to compute, with the surface integral of c ds over S2 is the surface integral of 0 ds over S2, which is 0. So now we just need our last surface integral. Let's see, surface integral over S3 of c ds. So that'll be double integral over d of 1 plus x times the square root of 1 plus each of our partial derivatives squared. So partial zx, partial zy squared, and that's equal to the integral from 0 to 2 pi, integral from 0 to 1 of 1 plus r cosine theta for 1 plus x, and then square root of 1 plus 0, because the partial of z with respect to x will be 1 for S3, and then partial of z with respect to y is just 0. There's no y's in our z equals 1 plus x for S3. So how about we use polar coordinates, r d theta. Notice it makes much more sense. We'll go from 0 to 1 for r and 0 to 2 pi for theta, because we're integrating over disk D. So then we get the square root of 2 times the integral from 0 to 2 pi, 0 to 1, r plus r squared cosine theta, dr d theta, which is equal to the square root of 2 times the integral from 0 to 2 pi, half plus 1/3 cosine theta d theta, which is square root of 2 times theta over 2 plus sine of theta over 3 from 0 to 2 pi, and that's just square root of 2 times pi. So notice it's a little bit nicer where we're able to have z equals a function of x and y, because then we don't have to compute a cross product. So now we have our complete surface integral over S, because we can say that that is just equal to the surface integral over S1 of CDS plus the surface integral over S2 of CDS plus the surface integral over S3 of ZDS, which is 3 pi over 2 plus 0 plus the square root of 2 times pi. And if we want, we could write that as 3 over 2 plus the square root of 2 times pi by factoring out the pi. So similar to the way that we calculated work using a line integral, we can calculate flux using a line integral if we define it using vectors. So first we say that if S is a surface that has a tangent plane at every point, x, y, z, except at any boundary point, and if it is possible to choose a unit normal vector n at every such point so that n varies continuously over S, then S is called an oriented surface, and the given choice of n provides S with an orientation. There are two possible orientations for any orientable surface. Either we have our normal vectors pointing outward like this, or we have the normal vectors pointing inward. So those are our two orientations. For a closed surface, that is a surface that is the boundary of a solid region E, the convention is that the positive orientation is the one for which the normal vectors point outward from E. This would be a positive orientation, and then inward pointing normals gives our negative orientation. So it's the same surface, just a different orientation based on where we choose to have the normal vectors point, either inward or outward. If F is a continuous vector field defined on an oriented surface S with unit normal vector n, then the surface integral of F over S is f dot ds, very similar to f dot dr. That was for work, so this will give us flux. So we define f dot ds to be f dotted with n ds. So this dot product doesn't really have any meaning until we say that it equals this dot product ds. We know how to calculate this integral, so because this will just be some scalar, and this will just be our regular thing that we throw in our surface area and parameterize and all that. So we can use that to calculate this new integral that we're defining. So if S is given by a vector function r of uv, then we have our surface integral f dot ds equal to the double integral over d of f dotted with ru cross rv dA, where d is the parameter domain. So let's prove that real quick. If S is given by a vector function r of uv, then n, our normal vector, is the cross product of that divided by the length of the cross product, because remember it has to be a unit normal. And remember, this will definitely be perpendicular to the plane with r and u and rv in it, because the cross product is perpendicular to both of the vectors that go in. So that's why it'll be a normal vector. So that means that when we calculate f dot ds, we throw in f dotted with this thing, ds, because it's f dot n ds, but ds is just written as the length of this cross product dA, so these lengths cancel. It's just like how we had the length of r prime cancel when we did our f dot dr integrals. So now we can use this. We'll find the flux of the vector field f of xyz equals zi plus yj plus xk across the unit sphere. So just be a little bit careful. Remember that this s over here, this ds, is the vector s, and this one over here is the regular surface one. So to be a little bit careful in notation to make sure that we're computing the correct integral. So we need to first parametrize our surface in order to do this. So we'll parametrize our unit sphere the same way we did in example 1. So we'll get that, let's see, r of phi theta is equal to sine phi cosine theta I plus sine phi sine theta j plus cosine phi k. And again, phi goes between 0 and pi, and theta goes between 0 and 2 pi. So that means that we'll take our vector field f, we'll evaluate it at this curve, this surface, r of phi theta, and we'll get cosine phi I, because remember it's zi, and we'll get sine phi sine theta for j, because y was just j, so it matches. And then, let's see, x was supposed to be k, so we'll just, basically x and c is swapped. So we'll have sine phi cosine phi k. Alright, and then, as we did in section 16.6, example 10, we will take the cross product of r phi and r theta, and we'll get sine squared phi cosine theta I plus sine squared phi sine theta j plus sine phi cosine phi k. And that means that our dot product f of r of phi theta dotted with our cross product r of phi cross r of theta will be equal to cosine of phi sine squared phi cosine theta plus sine cubed phi sine squared theta plus sine squared phi cosine theta. And let's do our surface integral now. So we'll have the surface integral of f dot ds equal to the double integral over d of f dot r of phi cross r of theta dA which is the integral from 0 to 2 pi, integral from 0 to pi of 2 times sine squared phi cosine phi cosine theta plus sine cubed phi sine squared theta d phi d theta, which is the 2 times the integral from 0 to pi of sine squared phi cosine phi d phi times the integral from 0 to 2 pi of cosine theta d theta plus the integral from 0 to pi of sine cubed phi d phi times the integral from 0 to 2 pi of sine squared theta d theta. Okay, this is awesome because this guy is 0. You can either evaluate it or you can remember that cosine looks something like this. So if you look at it from 0 to 2 pi, this cancels out with this. So that integral is 0. So that means that this entire thing is 0. So we get 0 plus the integral from 0 to pi of sine cubed phi d phi times the integral from 0 to 2 pi of sine squared theta d theta, which we compute the same way we did as in example 1, and we just get 4 pi over 3. In the case of a surface S given by a graph z equals g of xy, we can think of x and y as parameters and write f dot rx cross ry is equal to pi plus qj plus rk, dotted with minus the partial gx minus partial gy j plus k. So that means that our surface integral f dot ds becomes the double integral of this thing over here. So this is just an extra formula. We keep getting these whenever we have a nice graph. Our formulas always get a little bit better. We don't have to take cross products. So how about we evaluate this surface integral taking advantage of this? So what we'll do is we'll have to first draw our solid region E. It's enclosed by this paraboloid in the plane. So how about we try drawing the paraboloid? So let's say it looks something like that. We need a little boundary for this guy. Okay, and let's see if I can put some axes here. So this will be our z-axis, and then we need y and x. Okay, so then how about we split this up into base S2 and paraboloid part S1. So what we'll do is we'll assume that this thing has positive orientation to compute our f dot ds. So that means that the normals point outward, something like this. I'll draw another color for the normals. And even for the base, they point outwards, so that means they're coming out of the base underneath. Okay. So how about we parameterize S1, we'll do that surface integral, and then we'll do the surface integral over S2, which looks pretty easy because it's just the disk in the z equals 0 plane. So we'll have S1 given by P of x, y, z equal to just y, because that's what we're given for f of x, y, z. Y is our nth component, and q in this case is just x, and then r is z. But we have to write z in terms of the region enclosed by the parabola because we're trying to take advantage of the fact that z is a function of x and y. So we'll write that r of x, y, z is equal to z, which is equal to 1 minus x squared minus y squared. And now we have everything in terms of x and y, so we could take the partial of our functions z over here, so that'll be a partial of g, we're going to name it, as a function of x and y. So that'll be partial of g with respect to x equal to just minus 2x, because this guy will be 0, this guy will be 0. And then partial of g with respect to y will just be minus 2y. So let's see if we can compute our surface integral now. Let's see, surface integral over S1 of f dot ds. So that'll be the double integral over d of minus p times the partial of g with respect to x time, minus q times the partial of g with respect to y plus r dA. So that'll be the double integral over d of minus y times minus 2x minus x times minus 2y plus 1 minus x squared minus y squared dA. So that's the double integral over d of 1 plus 4xy minus x squared minus y squared dA. And it looks like it's probably easier to convert to polar coordinates to do this. So we'll say theta goes between 0 and 2 pi, and r goes between 0 and 1, because we're going over that disk. R goes between 0 and 1, and 1 stays 1, 4 stays 4. X times y becomes r cosine theta times r sine theta, so that'll be r squared cosine theta sine theta minus x squared plus y squared is r squared, and then dA is r d theta. So then this becomes the integral from 0 to 2 pi, 0 to 1, r minus r cubed plus 4r cubed cosine theta sine theta, r dr d theta, because I used up the r. I just wrote d twice. And this is the integral from 0 to 2 pi of 1/4 plus cosine theta sine theta d theta, which is equal to 1/4 of 2 pi plus 0, which is pi over 2. Okay, so that was our hard surface integral done. Our easy one is over the disk where z equals 0. So that means that over that disk we have surface integral over S2 of f dot ds equal to the surface integral over S2 of f dotted with, well, notice that ds is the normal vector that points down. It's f dot n ds, right? Since this thing is the z equals 0 thing, our vectors are pointing straight down for our normal vectors. So f dot n ds would just be f dot minus k ds. Notice that this is the vector s, this is not the vector s. I'm converting it so that I can write it as a double integral now. So this would be the double integral over d of minus z dA. Because this dot product or this dot product, the first two components I and j are just going to both be 0. So we'll just take minus the last component, which is minus z. And like I said, that's just 0. So this whole thing becomes the integral over 0 dA, which is 0. Wonderful. So that means that we'll add our two integrals together and we'll get the surface integral over s. So that'll be our flux. So f dot ds is equal to the integral over s1, surface integral over s1 of f dot ds plus the surface integral over s2 of f dot ds, which is pi over 2 as we calculated, plus 0, which is just pi over 2. So that's the flux. If E is an electric field, then the surface integral E dot ds is called the electric flux of E through the surface S. And then Gauss's law says that the net charge enclosed by a closed surface S is Q equal to epsilon 0 times that electric flux integral, where epsilon 0 is a constant called the permittivity of free space that depends on the units used. Another application is if we have the temperature at a point xyz in a body as U of xyz, then our heat flow will be defined as the vector field F equal to minus K times del U, where K is an experimentally determined constant called the conductivity of the substance. The rate of heat flow across the surface S in the body is then given by the surface integral F dot ds equal to minus K times the surface integral S del U dot ds. So if we have the temperature U in a metal ball proportional to the square of the distance from the center of the ball, then we can find the rate of heat flow across a sphere S of radius A with center at the center of the ball. All we do is put our ball at the origin, so then U of xyz, it says, is proportional to the square of the distance from the center of the ball. So we'll need some constant proportionality C times the distance would be square root of x minus 0 squared plus y minus 0 squared plus z minus 0 squared, but we're squaring it. So we'll square the distance, we won't have the square root, and we'll just have x squared plus y squared plus z squared. So then we have f of xyz equal to minus k times del u, which will be minus k times c times, well, the partial of this thing with respect to x will just be 2x, because we're taking our gradient, and then the partial with respect to y is just 2y, and then for z it's just 2z. So now we need our normal vector. So we could say that our normal vector, we want it to point outwards. So it points outwards in the direction of x, y, and z. So those are the components of the vector that points outwards. But we want it to be a unit vector. Remember that if the radius of the sphere is a, that means that x squared plus y squared plus z squared is a squared. The square root would just be a. So we just have to divide by the length of this thing. So we're dividing by the square root of a squared. So we're dividing by a. So we'll just have 1 over a times x for our I component plus y for our j component plus z for our k component. Because basically the length of any vector that points outwards on the sphere is just going to be the radius. We take the vector pointing outwards, that means that the components are x, y, and z. We divide by the length, so we're dividing by a. So then this implies that f dot n should be minus 2kc divided by a times x squared plus y squared plus z squared. And notice this is just a squared. So a squared cancels one of the a's, so we'll just have 1a left. So minus 2a kc. So that means that our surface integral f dot ds that we can use for our rate of heat flow will be equal to the surface integral, by definition, f dot nds, which is minus 2a kc times the surface integral ds, because this entire thing is constant, so we can just pull it all out. So this is just going to be minus 2a kc times the area of our surface. But that's minus 2a kc times the surface area of a sphere is 4 pi r squared, so this will be 4 pi a squared. So that's just minus 8 kc times pi a cubed